Okay, let's unpack this research because the implications here, I think, fundamentally shift the conversation around AI world models and robotics.
You really do.
We are diving deep into VDB2. It's an architecture that's, explicitly focused on building AI agents that can do genuine prediction and planning.
Right. And it's very much rooted in those predictive processing frameworks, like the work from Craig, Friston, and Clark that, a lot of people see as guiding human cognition.
Absolutely.
And I think for our audience who are already deep in the weeds of ML, our mission today is to really cut through the hype. We need a professional, comprehensive distillation of what's new here.
The methodology, the results.
Exactly. The novelty in V-JEPA2's methodology, the critical engineering that let them scale it, and of course the hard performance numbers. We're sticking strictly to what's in the paper.
And the high-level result is just what makes this so compelling. This architecture, VGPP2, it starts out as an action-free model.
Completely passive.
Pre-trained on just an absolutely massive amount of internet video.
But it's that two-step process that's the real innovation. You take that massive self-supervised foundation and then you transform it into VGPP2AC, the action-conditioned model.
And you do it with a shockingly small amount of robot data.
Just 62 hours. And it's unlabeled video from the droid dataset. The outcome of all that.
Zero-shot picking and placing. With Franca arms, in labs the model has never seen before.
That's the core question, isn't it?
It is. How do you go from 1 million hours of passive, just observation to high success, zero-shot physical action with only 62 hours of hands-on data?
If you've been watching the self-supervised space, this paper really answers how far you can push observation alone to build that foundational physical knowledge.
Precisely. So let's start with that foundation, the core novelty of the joint embedding predictive architecture, or GP. How does this approach work, and why does it scale better than, say, its generative counterparts?
It really all comes down to efficiency and focus. Traditional video generation models, they're trying to do this incredibly costly pixel-level reconstruction.
Predicting every single pixel in a future frame.
Right. The GLAD approach, though, it uses a visual masked denoising objective. So it predicts the masked segments of a video, but, and this is the key, it does so entirely within a learned, compressed representation space.
Not in pixel space.
Never in pixel space. And that abstraction is the secret sauce. Predicting pixels forces the model to obsess over high-frequency, noisy details, flickering artifacts, random reflections, the precise movement of every single blade of grass.
Things that are ultimately unpredictable and irrelevant.
Exactly. The JEPA objective intentionally filters that stuff out. It forces the model to learn representations that only capture the predictable aspects of the world, like an object's trajectory or its interaction dynamics.
It forces the latent space to encode a cleaner, more generalized model of world structure.
If it has to learn what matters to predict movement in that latent space, it has to learn some form of physics.
Okay, let's talk about the sheer engineering scale here. V-JEPA2 was pre-trained on the VideoMix 22M dataset. That's over 1 million hours of video.
And 1 million images. The scaling is just dramatic. The encoder uses a vision transformer, and they scaled it all the way up to a 1 billion parameter VITG.
And to get that to train stably, they had to bring in a new architectural ingredient, 3D ROPE.
Right, rotary position embedding, but applied across all 3 dimensions, time, height, and width.
So that shift, moving from the absolute synchros position embeddings to a relative encoding like 3D ROPE, why was that so critical for video models in particular?
Well, when you're dealing with massive video sequences, especially at higher resolutions and longer durations, those standard absolute position embeddings can really struggle.
With the long-range dependencies.
Exactly, and just the sheer volume of tokens, it leads to instability, particularly in the deeper layers. 3D ROPE just provides a much smoother, more effective way to encode the relative distance between tokens in that 3D volume, which is essential when you're predicting masked segments far into the future.
That makes perfect sense. The positional signal needs to be robust across time as well as space. Okay, so speaking of robustness, let's highlight the 4 big methodological contributions they found were essential for this to work at scale.
The first one is the most obvious, data scaling. They just dramatically increased the dataset size from 2 million videos up to 22 million.
But not just raw data dumping.
No, critically, they used retrieval-based curation on the YT temporal 1B data. It confirmed that quality really beats raw, noisy volume. That alone netted them a crucial plus 1.4 point average performance improvement.
Okay, number 2 was model scaling.
Yep, the linear performance gain continues to hold. Moving the encoder from a 300 million parameter VITL to the 1 billion parameter VITG gave them another substantial 1.5-point average improvement across the board.
Third was simply longer training.
Which is interesting because standard models often hit diminishing returns. But here, with this scale of data and model, extending the training from 90,000 iterations to over 250,000 was justified. It yielded another 0.8-point gain.
So the representation just keeps getting deeper. And the fourth point, this one's really about the compute cost and feasibility.
It is. Higher resolution and progressive training. This is a really elegant optimization. They found a strategy to progressively scale up both the temporal duration, from 16 to 64 frames, and the spatial resolution from 256 up to 384.
And this progressive approach, it's a huge deal for the GPU budget.
It is arguably one of the most important engineering contributions. Training at full resolution from scratch would be prohibitive. This strategy achieved an impressive 8x reduction in required GPU time. It's really the only way you make these massive models computationally viable.
So now we've established this incredibly powerful and refined V-JEPA2 encoder. Let's look at its performance.
Yeah.
How do you measure the quality of the concepts it has learned?
They follow the standard protocol. You freeze the encoder weights, and then you train a lightweight, 4-layer attentive probe on top of its representations for various classification tasks.
So first up, motion understanding. How did it do on benchmarks that require recognizing fine-grained actions?
It excelled, especially on something V2 or SSV2. And if you know that benchmark, you know it's tough, because it requires understanding subtle human interactions, not just identifying objects.
And the number.
V-JEPA2 achieved a strong 77.3 top 1 accuracy. It's solid validation that the predictive JEPA objective really does extract dynamic, fine-grained movement information.
And what about the other side of the coin, prediction? Specifically, action anticipation on Epic Kitchens 100.
This result is truly significant. V-JEPA2 set a new state-of-the-art result of 39.7 mean class recall at 5.
And for context,
To put that in perspective, that is a remarkable 44% relative improvement over the previous best model, Plausiviel, which is an 8 billion parameter model. The scaling and the predictive representation clearly translated into a superior ability to anticipate complex real-world actions.
okay, now here's where it gets really interesting for me, bridging that understanding to the abstract world of semantics. V-JEPA2 was pre-trained with no language supervision at all.
Right, yet they tested it on video question answering. And this is the strong evidence that the model learned genuine, transferable concepts.
It kind of challenges that conventional wisdom that you need language in the pre-training loop for a strong VLM.
It does. They aligned the purely visual VJA2 encoder with a large language model like a Quentin 2.7b using standard visual instruction tuning.
And the results were state-of-the-art in its class, the 8B class. I'm looking at 84.0 on perception test and 76.9 on temp compass. These are tasks that require complex physical and temporal reasoning.
Exactly. The quality of the visual representation learned just through self-supervised prediction is so high that the language alignment phase isn't teaching the model what an object is or how it moves.
It's just providing the semantic labels for concepts the model already robustly derived.
Precisely. The better the visual concepts, the better the final VLM. And they found that scaling up the alignment data pushed those results even further.
Okay, that brings us to the ultimate payoff. Taking this conceptual, observation-driven model and actually applying it to physical control. V-JEPA2 is action-free, so how do they make that transition to V-JEPA2AC, the action-conditioned model?
So they kept that powerful V-JEPA2 encoder entirely frozen, retaining all that massive generalized world knowledge. Then they introduced V-JEPA2AC by post-training a new, dedicated 300 million parameter predictor network.
And its only job is to learn the effective actions within that already rich representation space?
Exactly. And this is where those 62 hours of unlabeled robot video from the droid dataset come back. That's the entire training set for physical action generalization.
That data efficiency is incredible.
It is. And the post-training objective was carefully designed for stable autoregressive prediction. They used a combination of a teacher forcing loss and a critical two-step rollout loss.
The rollout loss being essential for robustness during planning, because planning is fundamentally an autoregressive process, right?
Absolutely. By training the model to predict 2 future steps ahead, even when only enrolling 1 step during the loss calculation, they minimize the accumulation of prediction error. It fundamentally enhanced the model's ability to do long, stable rollouts at inference time, which is just non-negotiable for planning.
So once it's trained, how does V-JEPA2AC actually decide what action to take? They're using model predictive control.
Right. Planning is done by iteratively figuring out the best sequence of actions that minimizes a goal-conditioned energy function.
Which is basically the L1 distance between the imagined future state and the goal image's representation.
Yes, in simple terms, it's asking, which action sequence, when I apply it to my current state, gets me closest to the goal image in the latent space?
And it optimizes that search using the cross-entropy method.
It does, in a receding horizon control loop. A key finding was that the V-JEPA latent space induced an energy landscape that was relatively smooth and locally convex. And that is critical because it means the optimization is efficient and doesn't get stuck.
Let's talk about the zero-shot control results, because this is the acid test. They deployed this on Franca arms in 2 totally different labs.
Environments completely unseen in the droid training data with no task-specific rewards. And they demonstrated robust generalization. For single goal reaching, the model consistently got the end effector within 4 centimeters of the goal.
And it's doing this from monocular RGB input alone.
It has effectively inferred the 3D spatial dynamics and the causal effect of its actions from those 62 hours of video.
And for the more complex prehensile manipulation picking and placing objects, the success rates are really strong. 80% for a cup, 65% for a box, average across the labs. Again, zero shot.
And this brings us to the ultimate computational victory, which is the speed. Let's compare V-JEPA 2AC to a video generation baseline like Cosmos.
A huge difference, I imagine.
V-JEPA 2AC achieved planning times of only 16 seconds per action, even when running a very robust optimization.
Whereas the Cosmos baseline, which plans by predicting future pixels, required a staggering 4 minutes per action.
For lower success rates, too, that difference is just massive. A 16-second action loop is slow, but it's viable for a lab. A 4-minute loop is just non-functional. The cost of planning by generating pixels is simply too high.
It solidifies the argument that latent space world models are the only computationally viable path forward.
I think so.
So to synthesize the overall contribution, V-JEPA is a major step forward. What's the core takeaway here for researchers?
The central contribution is really the successful derivation of these foundational representations from massive self-supervised observation. These representations are proven to be dual purpose.
Right, they work for high-level understanding and low-level control.
Exactly. They enable state-of-the-art performance in high-level vision tasks like anticipation, and they provide the highly data-efficient backbone you need for zero-shot physical control via model-based planning. It's a unified world model that successfully bridges perception and action.
That efficiency is the main message. The paper also outlined a clear path for future research. What are the logical next steps?
First, they noted the limitation of the planning horizon. The current models are good for short-range tasks, but solving complex, multi-stage tasks will require hierarchical models that can make stable predictions much further out than 16 seconds.
Second, the current model uses image-based goals.
Right. And given the successful language alignment they showed, extending the model to accept language-based goals is the obvious next step towards more general, human-specified tasks.
And finally, just continued scaling.
Of course. They saw consistent performance improvements up to the 1 billion parameter model. Finding new, scalable pre-training recipes for video encoders beyond that will likely unlock another generation of capability.
The success of this whole approach really relies on the model learning robust physics and causal dynamics from pure observation.
Absolutely. So consider this. What fundamental physical insights about mass, friction, gravity, object permanence, what must be encoded in that V-JEPA representation space to allow a model trained on only 62 hours of robot interaction to generalize zero-shot to entirely new physical environments and objects it's never seen? The depth of knowledge it derives from just passive viewing. That is the true scope of what representation learning accomplished here.